Good morning, everybody. So, I hope it was not too early for some of you, not too early for normalization. Just to bring you up to speed. Yeah, where did we stop yesterday? I, of course, as expected, didn't make it to the point that I had planned to come to, but at least I was able to motivate the idea of renormalization and to lay out a little bit of the strategy for you. And today we just, in one or two slides, I make it concrete for this toy model that I took, which was just a scalar field theory. So what is the most common practical procedure for renormalization? We have seen that corrections in perturbation theory, if you switch them on, will change the meaning of your parameters as you have already placed them in the original Lagrangian. And so we have to change them, to reparameterize them. And this is actually what gave the procedure a name. You have to renormalize your theory. And this means that all the parameters we had up to now, and even the field normalization, were kind of preliminary. And the official terminology for preliminary is bare. Yeah, these are bare in the sense of undressed parameters. There are no corrections yet in. And in order to make clear what these preliminary bare parameters are, they all get a subscript 0 in the following, and we will replace them by something that is not preliminary anymore. So let's do it here for the two-point function of propagators. We saw that the location of the pole in the propagator is tied to what we typically call a mass of a particle, at least if the particle can be really produced in the experiment, not like a quark, more like an electron or muon whatsoever. Then the location of the pole in the propagator is telling you really what the mass ruling the physical propagation of this particle is. So what we do is we take this preliminary mass, m0, and split it into one contribution that will play the role of this physical parameter. Yeah, let's simply call it a physical mass. I will refine this preliminary definition later, plus the rest. And the rest is just the difference between preliminary and physical mass, or between bare and renormalized mass, as we also say. So at the same time, to make really this two-point function in the propagator, in particular finite, and making it fulfill certain properties that we still have to define in more detail, we also introduce a wave function of field renormalization. That means we consider the original fields bare. We just have one, the field phi. I call it phi 0 here, and split it into a field that obeys certain normalizations times a rescaling factor. And for convenience, it's not just a factor that I call set phi, but I took the square root of it. The square root of it because naturally you approach the problem via the propagator, and the propagator is this green function that combines or that contains a product of two field propagators. That means I have two factors of such phi's, and then the square root goes away, and you just have this factor. So it's only a matter of convenience. Yeah, you see it here. Huh? Yeah, the propagator for the bare field is just set phi times what we call the renormalized propagator. I just put the set here to the other side. What we also know is that actually in lowest order, you don't have to do anything. That means the set factor here and also this so-called mass normalization constant delta m, so all the deltas, they come with higher order suppressions, which means we can write, for example, the set factor here as 1 plus a correction. And the correction just goes with a certain power of couplings times loop functions. So let's take these two transformations. We also call it a renormalization transformation. Let's plug this into the definition of the propagator and calculate this renormalized propagator in terms of now renormalized quantities. This is indicated here. So you see, I just introduced here a new symbol, sigma r instead of sigma. So before renormalization, including corrections, I just had the same expression with a sigma, and now I just define the renormalized version of this so-called self-energy to take care of these reparameterizations. And in the following, I just do this in one loop order. That means in a linearized order for all kind of corrections. And if you do it right, you see that this renormalized self-energy and the unrenormalized before are related just in this kind of linear fashion. So it is clear that if you switch off all the renormalization constants, you just have sigma, and the delta m and the delta z from here, they just give you additional pieces here. And they exactly have the form, if you look into the momentum dependence, as you expected to be able to kill or to absorb the divergences, because you have seen yesterday that these 2-point functions got divergences that go on the one hand with a p-squared factor and a constant. And you can adjust, of course, the delta m and the delta z in such a way that the new defined renormalized self-energy, in fact, is ultraviolet finite. So this is only having a first glance at the ultraviolet divergences. Of course, you have to do it in a more proper way, because you also have to control in a proper way the finite parts of this sigma. So how do you do that? We make use of the idea that m squared should be the location of the pole in the propagator, and we call this a physical mass. And if we insist that p squared is m squared, is bringing you directly to the pole, it is clear that the sigma r at this pole has to vanish, because then m squared is really the location of the pole. This is what is spelled out here. So we call this a renormalization condition. Actually, it's called the on-shell renormalization condition, because it ties the location of the propagator pole to the mass. So the mass is the on-shell point of this propagator. So this fixes this renormalization constant. You see, this part does not contribute here. And if we also want to achieve that the residue, that means on top of the pole, the numerator factor, is not changed by corrections. That means we basically keep the normalization of the field. Then this fixes this renormalization constant in such a way, because if you expand this here and calculate the residue, you see the residue goes basically with 1 plus the derivative of the self-energy. And if you demand this to be 0, then this fixes this wave function normalization factor to exactly this contribution here. So you can actually insert these results here back into the form of the renormalized propagator. You find it then here, and you see actually that if you expand the self-energy around the location of the pole, this is just then there should be a minus sign here. This is just then taking away the first 2 terms in a Taylor expansion around that pole. And if you make use of the knowledge of the divergences, you also see you can write it just in terms of the finite contributions from your original sigma. Finite means you just drop this delta term that I have introduced earlier. So that works nicely. We just have to do a similar thing also for the one coupling that we have in our toy model, which was this phi to power 4 model. We just have one prototype vertex in lowest order, which was ruled by this coupling lambda, which I now call lambda 0. To make clear, it is this preliminary bare coupling plus corrections. And the idea we want to apply is basically the same. The renormalization transformation is just splitting the bare lambda into a renormalized lambda and a renormalization constant delta lambda. And there are various ways to define actually the meaning of this lambda here. That's really something you should do with care. You can, for example, choose something that is technically very convenient, or what is maybe closer to experiment. You can think about an experiment in a certain kinematical limit, where you just call the measured cross section, the one that is ruled by your elementary coupling lambda. That means that you insist that after renormalization, for example, these corrections, they vanish at a certain kinematic limit, for example, forward scattering or certain energy point, whatever. So let's do it that way. You can call it kind of a momentum subtraction scheme. That means lambda assumes a measured value for a special kinematical point, which I call Px for experimental. And if you do that, you can in this way also define a renormalized version of these 4-point vertex functions as I introduced it yesterday, which gets a rescaling factor from the definition of the green functions. Here it comes as a z² factor. And if you also expand this into this delta z as before, you do this replacement here, then you see that in one loop order, you just have this renormalized version of this special green function. This is lambda plus contributions from renormalization constant delta lambda and delta z. Delta z is already known, plus your unrenormalized here, and delta lambda is still to be fixed. And if you fix it, as I've said, so that the whole thing here vanishes at this special kinematical point, which is singled out here, then you can solve for your normalization constant delta lambda, and you get it as a combination of the delta z and these vertex corrections that contain ultraviolet divergences, but these ultraviolet divergences just go into the delta lambda, and in this combination, you can easily see that they drop out. That means if you now call this combination here a renormalized vertex correction, you can write it as a difference of two finite pieces at basically two different kinematical points. The one you want to calculate, this vertex correction, minus the contribution where you have defined your lambda to be the renormalized coupling. So you see that in this way, you also render your vertex correction finite. This was one version of momentum subtraction. There are also others that you certainly have seen and maybe also used before. For example, the technically most easy prescription is going under the name MS bar prescription, which does not make use of any special kinematical point, but you just say by definition, I calculate basically my delta lambda exactly in such a way, but in the renormalization constant for this coupling, for example, I only keep the ultraviolet divergent term, plus a little bit of universal constants, and this is exactly this capital delta factor, triangle delta factor that I have introduced. So when, for example, you have worked out a renormalization scheme, like, for example, momentum subtraction here, it is very often easy to downgrade this to an MS bar renormalization just by keeping in the renormalization constant only the divergent terms. This also makes everything finite, but the finite pieces of your correction do not have so easily a direct physical meaning. Here it is just the meaning of the finite parts is taken in such a way that you know that in a special kinematical reason there is no finite regime, there is no finite correction. But for MS bar, typically everywhere there is one, and there is also still this scale mu in the game that I've introduced. And if you use MS bar prescription, the mu really enters physical predictions, and we call it a renormalization scale. Just to say this only once, but I will not say much more about MS bar prescription in the following, because it's not so heavily used in electroweak physics. So this is the general program, and you know hopefully how to apply it, and now we will apply it to electroweak theory, at least at next to leading order. So let's just recapitulate what kind of couplings we have there. There are plenty, actually. They're all end-the-loop corrections in various ways. So if you just compare it to corresponding calculations, let's say in QCD, in Electroweak theory, you always have much more diagrams. Yeah, but the number of diagrams nowadays is not really a problem. Typically, you switch to some computer algebra system, or you write your own code anyway. And if the computer is doing a thing once or 100 times, it's not so much a difference as long as the CPU time does not explode. So many couplings. You see, for example, gauge boson self-couplings, scalar self-couplings, all kind of mix between them. You have couplings of fermions to spin-1 fields and scalars. And you have also these Fadeev-Popov ghosts, which I have only briefly mentioned in the first lecture. They are auxiliary fields with no physical meaning, so they do not come with physical states, but they can appear in loops, in closed loops, for example. So giving you some examples, what you need very often is, of course, the electron self-energy. Whenever an electron is, for example, an external state, like, for example, it's happening when you look into observables for a plus and minus physics, you always have to calculate the self-energy and the renormalization constant that come from it. For example, the electron mass renormalization constant, and also for the field, things like this. Similarly, for the W boson, I've spelled it out here. You have also plenty of diagrams. And what we do, typically, in the screen functions, we exploit the spin structure of the corresponding fields to to parameterize these 2-point functions in an appropriate way, which means, for example, the following. Let's look into the W boson. We know the W boson field has or is carrying a Lorentz index. That means the green function and also this 2-point vertex functions, it has 2 indices, mu, nu here. So it is a tensor of rank 2. And I can always build it up from the intrinsic tensor of rank 2 that we have in field theory, which is the matrix and the momentum running through. But that's all possibilities that I typically have here. That means there's, of course, a piece that goes with G mu nu, and there's a piece that goes with a external product K mu K nu. And now one way of writing down the full vertex function is shown here, where I have singled out the lowest order piece here. Actually, I should have mentioned this is in this 't Hooft-Feynman gauge. That means this gauge parameters in the covariant gauge I have set to 1. Otherwise, there is an extra piece here, but 't Hooft-Feynman gauge is very convenient for practical calculations. And the corrections, of course, they have a piece going with G mu nu and a piece going with this K mu K nu. And one particularly appropriate way of spanning this rank 2 tensor is in this way, where I don't simply take the G mu nu with the coefficient, but I combine it with this K mu K nu in such a way that this structure is, as we say, transversal. Transversal because if I contract it, for example, with K mu, I get 0. So it's in this way, this rank 2 tensor is orthogonal to the alignment coming with a momentum K. And the rest is just here, this K nu term. So this is called the transversal part, and this is the longitudinal part. It's a covariant decomposition of the 2-point function. Similarly, you can do it also for the electron. The electron is represented by a Dirac spinner, and the 2-point function is something like the outer product of 2 Dirac spinners. If you think about rows and columns, it's basically something like not a scalar that you get by multiplying a row with a column to produce a scalar, like in matrix multiplication. It's the other way around. It's the column times a row, which builds up a matrix. So you can decompose this matrix into something that goes with P slash, where this is the contraction of the momentum with the Dirac matrices, and something that goes with a unit matrix. Much more is not possible. There is just one additional tweak, which comes from the possibility that gamma 5 shows up because we have a parity non-invariant theory. That means we have to take care of the possibility that there are still a gamma 5s also in the game, and I can write it in such a way that I have a p slash times a right-handed parity projector, p slash times a left-handed parity projector, and a unit matrix. Actually, I could also have introduced here a gamma 5 as well, but at least at one loop, the gamma 5 part doesn't contribute. So typically one writes it that way here. So this is introducing the specific self energies for these covariant pieces here in the full electron 2-point function, which will appear also when you calculate the normalization constants. The reason for this covariant decomposition here and also there is the fact that these coefficients, sigma here, they are really scalars and they can only depend on p squared. Whereas the full 2-point functions here, they are tensorial or even spinorial quantities. And it's of course much easier to deal with this scalar stuff here if you make use of the covariant composition. Okay, so you see it's quite something to calculate, but as I've said, with computer algebra, it's not so hard to do that. Okay, let's go from 2-point to 3-point functions. You get even more diagrams. For example, here we have the coupling of a W boson to an electron neutrino at the end. So you can, for example, read these diagrams from left to right. Then you have the decay of a W boson into an electron neutrino pair. And you see it's just plenty of diagrams you have to calculate. Another example is the Higgs photon-photon vertex, which, for example, is the thing you have to calculate if you want to have a prediction for Higgs to gamma-gamma, for the decay, which is very important experimentally, as you know. And you see it's even more diagrams. And there's no lowest order part here for Higgs gamma-gamma. It's a loop-induced process. So this means, for example, that if you stick with this one-loop calculation, there's not even a renormalization piece coming with it here, because there's no lowest order contribution. For loop-induced processes, you never have a renormalization contribution because you have no leading order piece to absorb the ultraviolet divergence into. Okay, so let's slowly go in the direction of renormalization. And we follow exactly the same strategy as before. That means we consider all our input parameters and also the fields as bare, meaning preliminary quantities. They all get this zero stuff here. And what kind of input do we have? I hope you remember. We have, of course, the electromagnetic coupling as an input, the gauge boson masses, the Higgs boson mass, all the Fermi masses, and the CKM matrix. That's one very convenient choice to parameterize the input and to fix everything in the standard model. So I take this set of parameters and perform this renormalization transformation. And for the parameters, this means I have to express all the bare quantities in terms of a renormalized version and a renormalization constant. And the renormalization constants, they all have this delta stuff in there. And you see for each of the parameters, I just introduce a delta of this parameter. There's this one exception for the charge renormalization, where I simply call the multiplicative factor here, delta Z E, the renormalization constant. This is all just convention. The idea is always the same. I split it into a renormalized part and a renormalization constant taking care of infinities. There is one thing I would like to stress actually several times here again, for example, and this is the fact that the weak mixing angle, and CW was the cosine of the weak mixing angle, is fixed in lowest order by the mass ratio of the W and the Z mass. And this means if I take the W and the Z mass both as independent quantities, the weak mixing angle is not an independent quantity anymore, it's a dependent quantity. And this means you cannot introduce, let's say, another independent renormalization constant for the parameter CW or also SW. Actually, several years ago, it was not so uncommon that some people screwed this up. That's the reason why I always emphasize this. So you have to respect this relation here. I come back to this later again. Apart from the parameter normalization, we also do this trick of rescaling the fields. And if you have fields carrying the same quantum numbers, the corresponding particles, or better, let's say the fields, they can mix. What does mixing mean in higher order? For example, let's take the photon and the Z system as the prototype of this phenomenon. If you're calculating, for example, corrections to the propagation of a Z boson, then you can easily form loops where the Z is coming in, it goes into a loop with anything, and then it can, on the other side, a photon can go out, because the quantum numbers are the same. No conservation law forbids this. And so just by iterating loops, you can have all kind of mixing. A photon goes into a Z, the Z into a photon, again into a photon from a photon, again a Z. So it goes forever. And you would like to redefine your fields in such a way that for a free or nearly free propagation, like a Z boson on its mass pole, this should not happen. That's the definition of the field. It's nothing physical, because if you really physically produce a Z boson, it will be a Z boson. But you would like to align in this field space your fields in such a way that this does not happen at the basis of fields, which means you define the fields in such a way that they don't build up these loops doing this mixing. Okay, the way to do it is indicated here. You can define the fields to prohibit this mixing of physical states that are created by doing a matrix normalization. And you remember that the Z and the A originally were introduced as linear combinations of the W0 and the B. So it is clear it's always about proper linear combinations, and as the normalization of fields is taking care of the fact that the normalization might change by switching on interactions. This matrix value denormalization is taking care of the fact that this linear combination that brings you from a W and a B to a photon or a Z gets also a bit changed by corrections. So you just have to find proper conditions to fix these prefactors. I come to this in a minute. So just to complete this, of course, there's also rescaling of the Higgs field, and also for the Fermi fields. Actually, if you look closer here, I have here these F primes that are summed over. So in a way, this is also a matrix value denormalization, taking care, for example, in the quark sector, of possible mixing of quarks between generations. I will not go into details. This is typically not so important in practice unless you do flavor physics, for example. And even there, you have different problems. This is actually something more introduced from a principle point of view, or just to make it really right, although in phenomenology it's not so important. So that was the renormalization transformations. Now we come to the conditions that we use to fix the renormalization constants. Mass renormalization, for example. We have done this already for the phi field, so there's not so much to do differently now. The idea is the same. The mass squared is tied to the location of the pole in a propagator. The only thing that you have to take care now is that our two-point functions look a little bit more complicated, because earlier we had a scalar field which just had one component. There was no mixed, no tensor valued stuff around. Now, for example, let's take the W boson or the Z boson as an example, we have two-point functions which are rank 2 tensors. And this rank 2 tensors, you saw it had the transverse part and the longitudinal part. And I think it's appropriate to look also into, at least formally, into a scattering where you see the propagation of one particle just also as a transition amplitude, one particle in, one particle out. Yeah, and the physical part of a scattering matrix element is, if you remember the LSZ picture, the contraction with the external wave functions. So, which means that if you only want to control this physical part of the propagation, yeah, you have silently attach a polarization vector, let's say for the W boson, which is what I did here. And only for this contraction of the polarization vector with this 2-point function, I insist that the corrections at the physical on-shell point are 0. The polarization vector has a distinctive property that it is orthogonal to the momentum running through. That means that the contraction of this epsilon nu with k nu is 0. And this is immediately telling you, let's go back for a second, that in this covariant decomposition here, when I contract this with an epsilon with a polarization vector, all this k mu stuff drops out, which means that this longitudinal part is not subject of this part of the renormalization. It will not appear. Okay, it's formally nice. Only the transversal part is really going into this condition. I think the battery is running low here. We were already here. So what do I have to do? I really insert just the gamma WW, which I have introduced earlier and shown you again. I insert it in this condition here and demand that I get 0 if the k squared is my physical mass m squared. It's 1 or 2 lines that you have to do. And what you find is that you can solve this condition for this mass normalization constant. It simply turns out to be, again, the self-energy at the on-shell point. You will realize this real part here, which I have sneaked in here. This is something there's still to clarify, let's say. It has to do with the fact that the self-energy for unstable particles develop also imaginary parts. This is something to talk about later, unstable particles. The reason why people introduced here the real part is that they thought it is a good idea to keep a mass parameter real. Because if I had not introduced the real part here, I would have also imaginary parts in there. The delta m would be imaginary. My original mass was introduced in the Lagrangian as a real parameter, which would mean that renormalized mass is a complex quantity. So people didn't dare this to do at the very beginning, because the mathematical field theorists are telling you, of course, you should not screw up hermeticity of a Lagrangian, because then your time evolution operator is not unitary anymore. Things like this then happen. But eventually it turned out that, well, to really take care of unstable particles in actual calculations, this is problematic with a real part. But for now, it's okay if you do only one loop calculations and you don't run into a resonance. That's the way to do it. Okay. You see, the principle is the same, but new difficulties, subtleties come in. So I think I almost explained everything that is part of the comments here. There's only one still to make, and this is the fact that this whole concept, of course, also goes through with some, let's say, slightly different formulas at the very end to fix the mass normalization constants. But this works for the Fermis as well. But for the quarks, you might feel a bit uneasy, because you don't have actually the concept of a free quark propagating. And so it's not so easy to say what is really the pole in a quark propagator when the quark is not really associated with a realized physical state. That's true. And so quarks are to be handled with care. For the top quark, this on-shell mass is very often used. Well, in electroweak theory, it's doing a proper job. But if you then go also to QCD, it's also calling a little bit for trouble. So what people do often with the quarks is that they don't take this on-shell definition of a quark, but you can also, for example, talk about MS bar masses with this MS bar prescription that I at least mentioned earlier. Okay, just to say this once, this will also not be the subject of the lecture as a whole here. Okay, I should do it by hand. So having taken care of mass renormalization, what about field renormalization? There are actually two different kinds of field renormalizations that I have introduced. You remember this matrix of field renormalization constants, and there are the diagonal ones, which really are of the quality that I have introduced it for the phi field earlier. They just take care of the normalization of the fields. And what you have to do, you just go again to these propagators and you fix these diagonal parts of the field renormalization in such a way that the residue does not get a correction. Yeah, the residue for the propagator pole. This is spelled out here again for, let's say, W boson set, but it also works for the photon here. There's not so much to say about it. What you see here basically is a correction to the residue. I kind of contracted with a polarization vector to take care of what we, in quotation mark, can call a physical part of a propagator, one that survives the contraction with external states, and insisting that this doesn't get a correction can be encoded in this equation here. The real part again is to keep the field renormalization constant real for reasons that would have brought a headache to people earlier. So if you work out again this condition and spell it out in terms of renormalization constant, you see that the mass renormalization constant, which you have already fixed, is part of the game, but actually the thing drops out against the self energies at this on-shell point. But the field renormalization that is not yet fixed gets fixed by this relation here, and you get this simple expression, at least at the one loop level. Again, like in the scalar field, it goes with a derivative of the self energy at the on-shell point. And this fixes all these diagonal field renormalization constants, also for the fermions. So what about these non-diagonal parts? Yeah, here, as I've said, you insist that there is no correction bringing you from, let's say, a physical Z boson or a physical photon to a photon or a Z boson. So you rule out this mixing when you have the physical propagation of a particle. That means when the particle with which you start is sitting at its on-shell point and is transverse in the sense that it has really a wave function in terms of a polarization vector, for example. This is just this condition here. And this fixes the two non-diagonal renormalization constants that you have, namely the ones where you have this Z factor AZ or ZH for the indices. Let's go back and locate this in the transformation. These are these two contributions here. Okay. And what you find, the one is tied to the mixing self energy that turns a photon to the Z at the pole of the Z boson, the other one at the pole of the photon. So it's really literally show up as you would expect this. So we are almost complete with the normalization. There are two things to fix. One is to return to the problem of the mixing angle, which is fixed by the mass ratio. So this was the way we did it at the basis of the Lagrangian for the bare quantities. And we now simply demand that the same relation holds also for normalized quantities. And this fixes also in a way, if you want to introduce a normalization constant for the weak mixing angle by, for example, saying I have my original weak mixing angle here squared, the cosine squared, CW0 squared. I split this into a normalized part and a normalization constant. Then these two relations fix this renormalization constant unambiguously just basically by the mass renormalization constant, because the two masses go in there. So formally, it's convenient to introduce this kind of parameters just to condense expressions, but nothing new is going in there. Yeah, likewise, of course, you can introduce a normalization constant for the sinus of the weak mixing angle, and the trick here is just to keep the relation there where sine squared and cosine squared always add up to 1, both for bare and renormalized quantities, and this fixes unambiguously also this delta S squared, which is it's formally convenient to have it. Yeah, question?
Since CW is a ratio of these two, so what is the need of renormalizing CW?
As I've said, it's only a matter of convenience. You need not do this, because when you, for example, have a calculation, either Feynman rules or full amplitudes, you can always eliminate your CW, you can eliminate by the mass ratio, and you have taken care of the masses, so there's nothing to do. But often you get shorter expressions if you keep for the ratio of the two masses, you just write CW for it. That's very often done. And if you have introduced these quantities, you can just keep your expressions a bit smaller. That's one thing. And also conceptually, if you go away from the standard model, it's just interesting to see what happens to this parameter, because it's connected to the so-called rho parameter, which was actually introduced into electroweak physics more on a let's say phenomenological basis as a ratio between neutral current and charged current cross sections divided by the respective mass ratio. And you see by chance, by a specific choice of the Higgs sector in the standard model, this is 1 in lowest order. And this is also tied to this mass ratio, and then this to give it a name, it's really handy, because you see sometimes better what's going on. You tweak a little bit, for example, the Higgs sector of the standard model. Okay, but at this point, you're fully right. You need not introduce this quantity. Okay, but you have to introduce a renormalization constant for the electric charge. Yeah, this is really in electroweak theory your basic coupling. And you need a renormalization condition, and you take over the same as in QED. And this is something that is really physically a very valuable concept. And the idea is, like in QED, you would like to define the electromagnetic coupling in such a way that if you go to low energy physics, atomic physics, for example, whatever you do, or solid state physics, you very often can devise an experiment that is able to provide a very precise measurement, like in superconductivity, Josephson contacts and things like this. You can, for example, determine the electromagnetic coupling to a very high precision there. And well, it is wise to think about the idea that we introduce the electromagnetic charge, meaning that coupling, in such a way that we have direct contact to low energy physics. And this is what the so-called Thomson limit is doing for us. Formally, it is the following thing. You just take this coupling, earlier as introduced as the 3-point vertex function, and you look into the situation that you have a physical electron scattering here, so it's sitting on its mass shell, and it's bouncing off a photon. And this photon has very low energy. And in this low energy limit, in a way, you can view into this thing here as a physical scattering amplitude. And you insist that in the limit where the photon momentum is 0, that this vertex function gets no correction. This is the charge, the on-shell charge renormalization condition in the Thomson limit. And that's also the way the charge is defined in QED. And we also take it over in the full electroweak model, and it really works nicely. And it means if you do it like that, the parameter E is exactly the fine structure constant, typically called alpha at some momentum transfer 0. which is measured to high precision. So if you turn this renormalization condition into formalities, it's a bit complicated. It's more complicated than you might think, because of the mixing between the photon and the set. And you also have to exploit gauge invariance in a clever way to really find an expression that is very handy for this charge renormalization constant. So in principle, you could also say, well, why should I do this? Because I just calculate the loops here. So I have just a vertex function, a 3-point function, and I can solve this relation for delta z. That's true. But you see here in the final result that I've quoted here, on the right-hand side, there is no vertex function. There's no 3-point vertex. It's only self-energies. So there is some magic going on that turns this 3-point vertex function into something that can be expressed in terms of self-energies. And the magic is gauge invariance. That's one thing to emphasize here. But to really derive this from first principles without, let's say, additional use of some explicit calculations like any kind of 3-point diagram is really not so easy. Until a couple of years ago, where I re-investigated this with Ansgar Denner, there was no really proof that was based only on first principles like gauge invariance and stuff. At some point, always people just did a little bit of a loop calculation and plugged it in almost silently. For example, writing down consistency relations, what we call ward identities, or in more general terms, Lafno-Taylor identities. Very often they verified it more or less by one loop calculation and took this identity further on in the derivation. But to really derive it without doing a loop calculation is tricky. Okay, but it works. And I will not make it to this part of this lecture. It was maybe 2 years ago or so. I also wrote down an all-order form of this relation, which just also bases the whole proof only on first principles without doing really a loop calculation. Okay, so for us, it's just nice to have this relation here. Why? There are two reasons why this is nice. First of all, if you want to prove, let's say, any theorem where charge renormalization goes in there, maybe some people among you know the Thiering theorem, which is stating that corrections to low energy Compton scattering totally die out. That means low energy Compton scattering doesn't get any radiative correction. It means that you field theoretically deal with all order relations here, and there you need also simple expressions for charge renormalization constant, things like this. So if you want to prove theorems, it's nice to have these simple expressions. Secondly, maybe you realize something here. Namely, I introduced here, or demanded or formulated charge renormalization constant for an electron. I could have taken, I don't know, a U-quark or something. Quark is problematic, but let's say a muon. And I would have gotten the same relation here for the charge renormalization constant. What I want to say is that the right-hand side here does not depend on the electron, but I started with the electron. This fact is called charge universality. That means the charge renormalization, and this, if you go to MS bar and talk about running of couplings and so on, what you get here for this coupling, basically, for the renormalized coupling, has nothing to do with the electron. It is really a property of the coupling as a generic coupling. Although I have started with a renormalization condition that uses, of course, any kind of charged particle. And this statement goes under the name of charge universality. It has nothing to do with charge quantization, so it's really something else. Okay, this was also the basis of this. Yeah, sure. It works also with a W. I don't dare to formulate this with a W, because it would force me, I would have to talk about an on-shell W again, unstable particles, trouble ahead. So, but in principle, you're right. I could have, if I would have been a bit more bold, I would have written down here a W boson. Whatever, yeah, you can take whatever you want. Okay, so this completes almost the renormalization of all the standard model parameters. There's still the CKM matrix, but I don't better not touch it here, because it's in all high energy observables that we typically calculate and correct in electroweak theory. Doesn't play a role. Yeah? It would play a role if we had this kind of flavor change and would investigate this, but doing the renormalization of the CKM matrix over many years is always kind of causing discussions in the literature, because it's not so easy to do, to interpret the result. Anyway, it's done in various versions. You can look it up. I will not cover it here. And with this, we are almost done. To make further progress, let me stop this part of the lecture here and just make some comments again on this tadpole business. So I told you that if I blindly calculate, for example, loops with one external line for the Higgs boson, I don't get 0. And this means that actually if I calculate a propagator from these 2-point vertex functions, I have this kind of reducible diagrams in the gain. So it is very appropriate to introduce kind of a renormalization that kills this kind of diagrams, in the sense that I would like actually also to generate a counter term parameterized by some renormalization constant for this tadpole here in such a way that when I call this a renormalized 1-point function for the X, that this is 0. Because then all these reducible blobs that basically go to nothing, they are all killed. You can do this, and there are various ways to do this. This goes under the name of devising a tadpole scheme. It's nothing unique, because it is simply reshuffling terms in such a way that whatever comes from this tadpole stuff is basically shifted to a different place in green functions. And there are various ways to do it. If you have, as I've introduced it here, only on-shell renormalization schemes like on-shell masses and this electromagnetic coupling, the Thomson limit, if you have this for your physical parameters, whatever you do with the tadpoles, the results for physical quantities will not change. It plays a role, and then I just leave it. If you, for example, use MS bar renormalization conditions for masses, running masses, then surprisingly, the tadpole scheme plays a role. So it's interesting to follow up on this. I also did it last year with Heidi Chehak in some papers again to also make a proposal how to do this in our point of view a little bit better. It would go too far. It's a very technical thing. And the reason why, with a good conscience, I can just leave it as it is the fact that if you just stick with the usually adopted on-shell conditions, it doesn't play a role. But it's always good advice to remember tadpoles are non-trivial subject. So if you yourself start to do calculations higher order in electroweak theory, at least you should know where the tadpoles go. Do they matter or not? And as I've said, it depends on the renormalization scheme for the rest of the parameters. So if you want to know more, either you contact me or you look into the slides. Now I think it's a good idea to move on and take the next step towards the calculation of observables, including electric corrections. So this should now be on. Yeah, very good. Actually, a bit late, but I start lecture number 3. We will not make it to the end today, but we can continue in the afternoon. About electric corrections. So what I wanted to guide you through here are specific features of electric corrections that have sometimes even no counterpart in QCD. First of all, as an intro, I talk a bit about the relevance of electric corrections. Where do they matter, where not, and why do they matter? And one thing I think also Ilaria will take care of this are input parameter schemes. You have to actually to open this kind of worms again. What kind of parameters do you take from measurement and plug it in as an input in your predictions? Because the size of the correction sometimes very sensitively depend on it. Then you have photon radiation, which can drive corrections high. We have seen this already, or I have mentioned this for this initial state radiation for A+ and minus, for example. And if you go to very high energies, TV range or so, you will also see that electric corrections, they get blown up, and this also has a reason. And very finally, and this is something maybe for the afternoon, you have really to dig into the problem of unstable particles in quantum field theory if you want to calculate corrections to a resonance process. You saw that if you just do perturbation theory there, the resonance is just a pole, it's infinity, which is utterly unphysical. Cross-sections are never infinity. So let's start just with a prelude. Why are electric corrections relevant? How large are they? And so on. So precision measurements at the LHC. Let's talk a little bit about accuracies and precision. For example, what about cross sections? For example, for single W and Z production, this example I will be able to cover in the afternoon, I guess. Of course, there are uncertainties on the it's not exactly on the experimental side. It's somewhere in between, with the parton luminosities. When you want to make contact between hard scattering and measured cross sections, you have to know the luminosity of the protons, which turn, show up in the hard scattering as quarks. And so the luminosity itself has a couple of % uncertainty just experimentally. If you turn the luminosity of the protons into some kind of parton luminosity, typically quantified in terms of parton distribution functions, they also come with accuracies of a couple of %. There will be a dedicated lecture, I think, by Maria Ubiali. You learn much more about this. But this is telling you that if you just talk about cross-section measurements at the Hadron Collider, there are limits. You have the problem that you cannot exceed this kind of precision, but still, % precision is great. But I want to know in how far electric corrections are relevant, and they typically go, let's say, relative corrections with alpha over pi, or alpha over pi over sine squared of the weak mixing angle. This is something of a %. So actually, you would naively say, not so relevant in view of these uncertainties. But if you look into the shapes of distributions, if you normalize them, then you normalize away much of this uncertainties here, and you often have shapes of distributions that are known at the % level, or if you form ratios of cross sections, also this luminosity, and to some extent maybe also the PDF uncertainties, they almost cancel out, or they are at least damped a lot. So this is bringing you into the ballpark where the electric corrections, just by counting couplings, play already a role. Secondly, there are also high precision measurements of specific parameters. I call them to some extent also pseudo-observables, which are carried out at Hadron Colliders, like the W boson mass measurement or this effective weak mixing angle. And if you look into the relative precision for these quantities, you have something like 10 to the minus 4. So this is really extremely precise, and the electric corrections are really at the heart of what you have to control on the theory side to make this possible. And if you go, for example, into the TV range of transverse momentum, transverse mass, or whatsoever, or invariant mass tails in distributions, you always, you very often have the possibility to go to the position of a couple of percent. And I told you already that there are special mechanisms that make electroweak corrections large there. That means they really matter. It's not enough to look only into this play with numbers where you just calculate, let's say, or you take the size of alpha or alpha s. Naively, you would just say, okay, order alpha, which is next to leading order, typically in electroweak theory, this should compete with next to leading order in QCD, which is something like percent level. There is some truth in it. So you can say whenever next to leading order QCD is relevant, you should also worry about electroweak corrections. But this percent is way undershooting the size of electroweak corrections in special situations, for example, for photon emission, where you have kinematical reshuffling of events, for example, near some shoulder of cross-section or resonance. If you have a steep fall of a spectrum and you a little bit shift an event, you see you have a large effect. If you can redistribute a lot from the top of some shoulder or resonance down to a region where there is almost no event. If you just reshuffle a few of them, you get a huge effect in the tail of the distribution. That easily gives you 10, 20, even more percent corrections just from photon radiation, which is yet former enhanced by logarithmic mass singularities, for example, typically for a muon mass over momentum transfer Q times an alpha. This is a large factor. And I've mentioned already these high energy enhancements, which are due to soft and collinear exchange and emission of W bosons. Maybe I can come to this later. Okay. The wrap up here is just electroweak corrections are not as small as they might seem, and certainly important and relevant. So, peculiarities of electroweak corrections, just to motivate more of the rest of the lecture. Apart from this photonic stuff and high energy corrections, you have often very large so-called universal corrections, and they are connected to this, what I will discuss under the label input parameter scheme in a couple of minutes. That means this this charge renormalization constant delta ZE that I have introduced, if you start to calculate it, you see already a little bit of trouble going on there. There are large corrections in there. And how they combine with the other corrections in your process plays really a role what kind of electroweak corrections you get at the very end. So this is clarified and further elaborated on under the label electroweak input parameter scheme. I also mentioned that the instability of the W and Z bosons is something to properly take care of if you want to describe a resonance. And very finally, something that I will certainly drop from this lecture is that it is also not so easy, for example, to identify a photon in a hadron collider environment. This goes under the name photon jet separation. Let's just make this clear at the basis of one example. Think about a quark that you produce in a hadron collision, and the quark is radiating in a collinearly enhanced way a photon almost in the same direction. So what's finally, of course, getting dumped in a detector is something that is triggered by the photon. In the electromagnetic calorimeter, there will be a little bit of a shower, and the quark has to go somewhere. So there must also be a little bit hadronic activity there. But what kind of picture dominates, it's not so clear, because the quark can almost transfer its whole energy to the photon. Then you see basically a big photon signal in the electromagnetic calorimeter and a little bit of hadrons, or you see several hadrons coming out. That means the jets, which also has some kind of more photon activity in the electromagnetic calorimeter. Of course, there's a transition region between the extremes. And at some point, you have to decide, do I count it as a jet or do I count it as a photon? Naively, if you just did QCD, you would say, I don't know. The photon is also part of a jet, and I call everything a jet. Could do that. That's theoretically very clean, but this is not what you want to do, because you want to do photon physics. You want to isolate processes with hard photons. So you would lose a lot of phenomenology if you just blindly said, well, photons are part of jets and that's it. Yeah, it would be theoretically very clean to do it, but it's not what you want. And to do this separation properly brings in more trouble. And one way is, for example, introducing fragmentation functions, which are kind of parton distribution functions for final states. So another non-perturbative object. So this is something I would not like to talk about in the following, just because of reasons of time. Yeah, input parameter schemes. Let's start with something very serious. What is the issue? Typically, in your natural way of defining the input parameters, as I've said, you take the gauge boson masses, the Higgs mass, Fermi masses, CKM matrix doesn't play a role for us. You have to fix the alpha and alpha S. Alpha S is something for QCD people to take care of. Not my business in this lecture, but the alpha. What do I take? I can take the fine structure constant, or I can actually take an alpha taken from any kind of more high energy driven experiment. There's also the concept of a running alpha. I come back to this later. And if I take this, for example, the effective alpha at the C pole, I would have a 1/129 instead of 137. If you just take the difference here, that's something like a 6% difference. So what does it mean? Yeah, if I have the choice to do either this version or this one. If I take my on-shell renormalization scheme as I have defined it up to now, I would have to take the alpha 0, but I can reparameterize in a way my theory, which brings in a little bit of a finite part of a normalization constant. But this finite part that I shift around is 6%. So this means the following. If I make a prediction with this scheme in leading order without any normalization, or in the second line here, I get a leading order prediction that changes by 6% for each power of alpha in the cross-section that I have. This is huge. So if I, of course, calculate higher and higher orders, the difference has to go down. Yeah, because finally I have to converge to a unique prediction, which is clear. But the perturbative stability of my prediction is something to keep an eye on, because if I include only, let's say, next to leading order corrections, I repair the 6% difference, but not the, I have no control over the two-loop stuff. So 6% times 6% times the number of alphas that appear is easily something that is, again, a couple of percent. At least 1 to 2% or so. If I want to control this, you see, it's a good idea to adjust the alpha that I use to parameterize my leading order prediction in such a way that I make the rest of the corrections as small as possible. And this is what we typically call the choice of input parameter scheme. Do I take alpha of 0 as an input, alpha of mz, or I can even take G mu, because I can solve the relation between the muon, between the Fermi constant and the rest of the Electroweak parameters. I can also solve it for alpha, and this is what we call alpha G mu. If you do that, you will find it's something in between here, something like 1/132 or so, which is something like a 3% difference between either of the two values here. Yeah, so it's, well, very appropriate to think about the way of you fix alpha in your leading order prediction to make the rest of the corrections as small as possible. So already here a couple of warnings. What people a longer time ago actually did sometimes is to say, well, I have a lot of diagrams that go in my prediction. And here this looks like a QED diagram, that looks like a weak diagram, blah, blah, blah. So what they did, they just adjusted in each diagram in the way they liked the couplings to come seemingly as close as possible to the experiment that fixes this type of coupling. And what you get is a totally inconsistent answer, because you cannot simply fiddle around in each diagram with the parameters that parameterize the diagram, because there is crosstalk between the diagrams to really make a consistent prediction. There are things to respect, like gauge invariance, unitarity, if you have higher order corrections, ultraviolet finiteness, things like this. You totally screw it up if you blindly optimize couplings here and there. I even remember, okay, it was outside the standard model. I remember, for example, SUSY calculations, which were just advertised. I find 30% corrections coming from SUSY. No wonder, because they screwed up parameter dependencies. And what finally would have been the right answer was 1% or so. Yeah? So you can get totally wrong stuff if you break consistency. So this is something to keep an eye on. And how to do it, for example, is if you really want to break up amplitudes, you have to do it with great care. And one way to do it, for example, if you know you have, let's say, gauge invariant subsets of diagrams, then you can just rescale the subset in such a way that you even take different values of alpha, but only as global factors. And you have to do it consistently. That works, and sometimes it's the way to do it. And finally, again, reiterating on this point, the weak mixing angle is not a free parameter. Don't change it blindly. And likewise, also Yukawa couplings, they are uniquely fixed by Fermi masses. What people, for example, in QCD often do, because there it's legal, they treat a Yukawa coupling as a free parameter and tweaking things there in such a way that they can minimize corrections. Don't do it so easily in the Electroweak theory, because there is crosstalk between the Yukawa coupling and the Fermi mass. It's basically the same thing. Okay, so you see, there are many ways how you can make things inconsistent. Coming back to alpha. So what's the problem? If you calculate the charge renormalization constant, and you go back to what I have shown you, you have to look actually to combine results from different slides. You see that in here, it's all coming basically from diagrams like this. You have to calculate this diagram for zero momentum transfer, so that in one loop order, there's basically only the mass of the Fermi surviving here, in particular also for quarks as indicated here. So if you just calculate delta ZE, start to do a calculation, you end up either with divergences if you use massless quarks, divergences that are not so easy to control, or if you take quark masses, you see a sensitivity to light quark masses. And I told you already, whenever this appears, you should get alarmed, because actually that's the sign that you have non-perturbative corrections in there that you don't control so easily. Similarly, such terms appear also in the photon wave function renormalization constant. And so you have to make sure that the way they go into your calculation, into a prediction, it should be in such a way that these quark mass logarithms drop out, because otherwise you're kind of really build up some sensitivity to non-perturbative physics. So this is the things you have to follow and to look what's happening. So these quark mass logarithms, they actually stand for a piece of physics that you can phenomenologically really get from data. And typically these quark mass logarithms, they are connected to a quantity that we call delta alpha. So what is this delta alpha? I introduced already at least silently a running, here I have spotted it or put it on the slide. I have introduced also a running version of the electromagnetic coupling, which is in a way almost something like a photon propagator that goes away from the photon pole to some finite momentum transfer q squared, where the q squared is called s here. So in a way, you control here the energy dependence of this loop, and this shows up very directly, for example, in the plus and minus annihilation going into hadrons. So what was measured with high precision is, for example, the ratio of the cross section A plus and minus goes to hadrons over A plus and minus goes to muons. Yeah, this R ratio, you have certainly seen this in several occasions. And these propagator corrections from the photon that go in there at low energies, they develop resonances. Yeah, like, I don't know, J psi and these BB bar resonances, the upsilons, all this kind of stuff. You have no chance to control this perturbatively, and this kind of part is the source of this quark mass logarithms. But you can measure it, and in a way, what you measure here is this ratio basically. And by some dispersion relation, I don't go into details here, you can tie this ratio actually into the momentum dependence of these propagator corrections. And this is actually what this alpha S is parameterizing. So this means that this low energy transfer and this running of the alpha this you can get from this R ratio measurement by dispersion relation. And if you go down to momentum transfer 0, you just have the alpha 0, and if you just cross all the resonances to several GeV, okay, most usually when we go directly to the C boson, we have alpha of MZ, and what lies in between is the effect of the resonances. That means if you compare alpha of MZ with alpha of 0, there is in an integrated fashion just the correction of the non-perturbative corrections of the running in there, and this is our substitute for the logarithms, or the other way around. The quark mass logarithms exactly stand for this piece, but this piece you can get from experiment, and this is called delta alpha of MZ. Actually, sometimes there is the hadronic added on here, yeah, which means it's only the effect from the resonances here. This you can measure. It's this kind of 3% thing. So which means we can really take either alpha of 0 or alpha of MZ as an input, and the difference is really a measured quantity. And by taking either alpha of MZ or alpha of 0 as an input, we shift around this non-perturbative piece. So by a scheme change, you can shift around and this logarithmic piece for the quarks here. I told you that sometimes there is an alpha hadronic in contrast to the delta alpha. The difference is just the effect of the leptons, which you can calculate perturbatively. So no problem. We can just talk about delta alpha. Okay, maybe this was a bit confusing how I explained it. For the practitioner, it means just the following. If you just take our predictions for delta ZE and delta ZAA, the quark mass logarithms, they can just be represented by the measured delta alpha. And they just show up in next to leading order in this fashion. And it's a good idea to take either one scheme or another just to kill this delta alpha from the corrections, because then you have absorbed the 3%, or actually a multitude of it connected to the power of alpha that is relevant. Now you have absorbed these large corrections into leading order if you have killed this in your corrections. So let's look in more detail how this works. Before we do that, actually, I should also mention another type of universal corrections coming with a rho parameter. yeah, what is this? I mentioned at least the name. And the idea basically is the following, that if you just look into the structure of these corrections, and Feldman was one of the first to do that, you see that whenever you kind of break symmetries, often you get large corrections, meaning, for example, for this case here, that the mass difference between the B and the top quark plays a particular role because they are sitting in the same doublet. And of course, you get a higher degree of symmetry if they have the same mass. But if inside the doublet there is a mass difference, which is quite large here, this kind of prohibits the cancellation of a particular type of corrections, namely the ones that are enhanced with the square of those masses. So what I want simply to say is that this leaves the trace that if you calculate this difference of self-energies normalized to their masses, and you just take low momentum transfer with respect to the top quark mass, you finally get a correction which is called delta rho top, because it's only the top term here, that is enhanced by a top quark mass squared. If you calculate this, is just another 3% or so. And it's exactly the combination that goes also into the renormalization constant that I introduced for the weak mixing angle. Yeah, that was exactly this. It's something like delta mz squared over mz squared minus delta mw squared over mw squared. And this type of correction you actually also would like to absorb in your leading order prediction, because it's again a source of several percent. Okay, let's keep it like that. I have to make things a bit short. So where do they appear in particular? Just to do a little bit of Fano already at this point, in particular in muon decay. We have seen this quite several times. So what we can do, we can compare muon decay in the Fermi model and muon decay in the full standard model. Actually, if it comes to the determination or the definition of this Fermi constant, what you do actually is you calculate in the Fermi model plus QED corrections, meaning photon emission, and in the full model you have your leading order prediction plus all electroweak corrections, including also photon emission. So if you just set the two predictions equal, you can write this equality in this way here. Now, on the left-hand side, you have the lowest order expression actually that resembles the alpha in the full model. This is what I called earlier alpha G mu. And on the right-hand side, you have alpha 0 times this correction factor delta R, which takes care of all radiative corrections to muon decay in the standard model minus the QED corrections from the Fermi model. And this delta R, if you do the math, you see it has at one loop piece that goes with our delta alpha that I've introduced, with the delta rho and the rest. And the hierarchy of corrections is, this, as I said, 6% of delta alpha, 3% of the delta rho, and the rest, which is just at the percent level and has a little bit of fixed mass dependence in there. So one way of exploiting this before coming back to the input parameter scheme is, as I've said, to solve this for the W boson mass. The W boson mass also go in here, so you can, for example, do it numerically. And by taking really the delta alpha as input instead of this logs of the quark masses, you can really make a solid prediction for the W boson mass. This is shown almost here. This is just the diagrams that go in there and a little bit of references that go to the physics. So what people did already 20 years ago or so is just to make a prediction of the W boson mass. For example, independence of the Higgs mass and also the top, but the top quark mass was already fixed at that time to an experimental value. And what you see is a standard model prediction in red for MW. Just this band here, you see a logarithmic depends on the Higgs mass, and the rest is parametric uncertainty here. And this at some point should meet actually the measurement. At that time, this was the W boson mass measurement. And this already pointed, as you see here, to a Higgs boson mass in the range of 100 GeV or so. So this is part of this Electroweak precision program that started already at lab times. So nowadays, we have the situation as follows. The full standard model fit, including the knowledge of the Higgs mass, is producing this gray band here. And in blue here you see plenty of W boson mass measurements that are compatible with this measurement. And actually they contribute to this fit here, apart from one result here, and this is from last year, this famous CDF determination with the smallest single error on the W boson mass. So there is big controversy going on about this measurement. And while we are among theorists here, I think they both screwed up in the experimental analysis, in the error assessment, and they ignored 20 years of theoretical progress. So maybe it's no wonder that there's trouble ahead. Okay, to be fair, there's of course more to be said about this. But this is under discussion. So I don't know whether they will reanalyze it or not. But I just show it as it is, with this nice summary how a piece of precision physics is actually made. And my point here, why I place it here, is that this delta alpha measured from this cross-section ratio is a very important input here. And you see it's really non-trivial to take care of this. And it's a large effect. So where does it leave us in terms of input parameter scheme? Let's bring this at least to the end. So what is the aim of the choice of the input parameter scheme? The aim is to absorb the universal corrections from delta alpha and delta rho as much as possible into leading order predictions in order to minimize, for example, their effect in 2 and higher loop orders. So let's play a game. Namely, we just look into a cross-section, which in next to leading order looks as follows. I have a leading order prediction, a leading order. I did not call it sigma because I extracted this prefactor from all the alpha dependents. Alpha to power n, capital N. This has to do with the number of external particles, the number of electroweak couplings going in there. Actually, there are n electroweak vertices that go into the leading order diagram. And I have, of course, the next leading order corrections, which is of order alpha. So what I want to assume is that this is the cross-section of some generic process with an energy scale, at least at the Electroweak scale, maybe a bit higher, not a low energy process. What I also assume that I have maybe n gamma external photons. And I assume also, this is also important, that I can separate them from any kind of low virtuality off-shell photons that split into fermion anti-fermion pair. So I really can detect, I can isolate these photons. Just an assumption, sometimes true, sometimes not. And I have NW couplings of W or Z bosons in the dominating leading order diagrams. The difference between neutral current and charge current couplings I will ignore in the following. For the leading effects, the set is almost coupling like a W boson, what the universal corrections is concerned. So I have NW factors of the gauge coupling G2 in the leading order amplitude and G2 squared in the leading order cross section. So with these assumptions, I can just write down the contributions to the next to leading order corrections that contain these universal pieces of corrections. For example, here in the alpha 0 scheme, I can look into the universal corrections of delta Electroweak. I get 2n times the charge normalization constant. I get n gamma times the photon wave function normalization constants. And I get minus nw times this delta S squared over S squared, which contains these rho parameter corrections. The point is, I just want to know whether this delta alpha and delta rho survive in my correction here in any of the possible input parameter schemes. So let's do it in the alpha 0 scheme. I know where the delta alpha is coming from and the delta rho. I just want to make it short. So I get, well, this universal contribution, and the scheme alpha 0 is ideal if this thing doesn't exist. That means if n is n gamma or n gamma is n, this doesn't appear, and if I have no electroweak couplings, that doesn't appear either. So the question is, are there any processes fulfilling this? The answer is yes. For example, at high energies, I can, for example, have photon-photon going to electron pair, W pair, or I have high energy complex scattering, then the thing here doesn't exist. It's 0. That means the alpha 0 scheme is describing these processes at high energies best. Huh? All these 6% corrections or so, they are gone. When I switch to the alpha of MZ scheme, I get an additional contribution from this delta alpha, just by the switch to the other scheme here. And this means this thing is cancelled here. And I can ask myself, are there processes in which this scheme works best? Yes, the n gamma must be 0 now, and W also must be 0. Okay, I have a little bit of a problem here, because there should be some coupling in there. This would mean that there is no process at all if I take this literally, but I can also have processes, for example, where photon exchange dominates over Z exchange. And this means effectively this thing here is small. And for example, if I have a plus and minus going to lepton pair a little bit below the Z resonance, this is such a case. Then I would call this not alpha of MZ scheme, but alpha of Q scheme. If I take alpha of Q or alpha S, I called it earlier, to parameterize the corresponding cross-section. As I've said, for example, plus and minus to lepton pair, or also Trellian production below the resonance, that would be ideally described by this alpha of MZ scheme. In a G mu scheme, there is also there's this delta R that is changing my relative correction. So there's also a top piece that gets changed, and I get this universal correction, and I see this thing is 0 if I have no external photon, and if N is NW, that means if all the couplings are really weak couplings, and gamma 0 and W is ideal. That means, for example, for W or Z decays, or all electroweak processes which are not dominated, which have no external photons and are not dominated by photons, are described ideally by the G mu scheme. Then there, the universal corrections are 0. So there might also be mixed cases where, say, I just take different alphas with different powers here, and this gives me yet another possibility to adjust this lowercase n and m in such a way that the universal corrections are 0. Okay, so maybe ignore this note here. I just close here with a plot that hopefully illustrates best what I wanted to say. So this is the relative from an older paper of mine, the relative correction to a Platonic process, namely this one here. It's the prototype process for Trellian. And the Z resonance is sitting here at 90 GeV, roughly. What you see here is only the weak correction, because this is the stuff that is sensitive to the universal corrections. What is the difference between left and right? On the left hand side you have U quarks, on the right hand side you have down quarks, which are the quarks that fuse to a C boson. So what we see here is that there is an offset between these three sets of curves. The offset is 6%. Yeah, this is what I told you earlier. That is just the 6% that I shuffle around by changing from the alpha 0 to the alpha Z scheme or to the alpha G mu scheme. Actually, it is 2 times 3% because this power of alpha that plays a role is power 2. Yeah, it goes with alpha squared. So the difference actually between the alpha 0 scheme and the MZ scheme here is the difference between red and green. The difference is 12%, which is huge. And it comes from 2 times 6%, it's twice the delta alpha. So you see, for very high energies, none of them is ideal because 0% would be here. This would be ideal, which is exactly what the G mu scheme is providing, where I interpret the couplings simply as truly weak couplings, let's say. So for the high energy tails also here, the G mu scheme is doing the best job, which is exactly what my game with the universal corrections is suggesting. If you go far below the Z resonance, actually it's more a process that is dominated by photon exchange. And this means that actually all of a sudden here, this alpha of a Z scheme, here, the green one, is better suited because it's closer to 0. So there's a transition region even on the energy scale, which scheme is best. Yeah, so this is also suggested by the game that I played before with the universal couplings. Okay, so I just bring this example to kind of illustrate my point. There's also something that you hardly see. It's always a pair of curves, and the solid curve is just the next to leading order correction, and the dotted curve next to it is including the leading two loop corrections. And you see the difference between dotted and full. It should ideally be small because this would mean you are stable against large two loop corrections. And again, you see here that the difference is smallest here for the G mu scheme and here for the alpha of Z scheme. So this was my motivation, to make the prediction as stable as possible with respect to corrections that I have not yet fully controlled. Okay, I know it was a bit quick. The technicalities might not have settled down everywhere with you, but I think the interpretation and the aim was kind of clear. So we are already late. I have to stop here, and maybe we can take quick questions still, 1, 2, or during the coffee break. I don't know.